Hello there. In this video, we're going to talk about complex numbers. Now, complex numbers was a concept I introduced way back in my very first video when I talked about number systems. And I referred to it being the set of all numbers that are in the form a plus bi, where a and b belong to the set of real numbers, and I is equal to the square root of -1. So let's talk about where that comes from. I'll start with a couple quick computational problems. Solving for the square root of 36, that's easy, we know that to be 6. Square root of 100, that's easy, we know that to be 100. Oops, glitch. So that is equal. Square root of 80, this was a problem I simplified back in my simplifying radicals video. This equals the 4 times square root of 5. Okay? But this naturally begs a question. So I'll use 36 as an example, but you can do this with any number. Name all the square roots of 36. And what this stems from is if we had an equation where we squared a number and we get 36. What numbers can I square to give me 36? Well, naturally the inclination is to say, okay, I'm going to take the square root of both sides. The square root and the square cancel, so I end up with x, and then I get 6. And that's true, because 6 times 6 equals the 36. However, note that -6 times -6 also equals 36. So when we're solving an equation like this, when we take the square root of both sides, our final answer will be plus or minus 6. Now, let's really quickly distinguish these two. The answer for x squared equals 36 will be x is equal to plus or minus 6 because they're both solutions to this equation. However, with this first problem that we did, we're talking about just the principal square root, which is just 6. So when you're just simplifying a computation, the answer is 6. When you're solving an equation, x squared equals 36, that's when we put the plus or minus in there. So naturally, this brings up the question, what's the square root of -1? This is a question that kind of stumped mathematicians for centuries, because if we think about it, we go back to the 36 example, 6 times 6 equals 36. A positive times a positive equals a positive, but we also get -6 times -6 equals 36. So a negative times a negative equals a positive. Now, what we can do is talk about how we could do a negative times a positive, but that defeats the purpose of squaring a number because they would not be the same. What instead we do is think about, well, maybe let's say I wanted to find the square root of -36. Okay, I know that this is square root of -1 times 36. And then I can use my property of radicals to separate this, and I get square root of -1 times square root of 36. And I would simplify this to be, I'm going to write the 6 first and then times the square root of -1. And since I don't know what the square root of -1 is, I can leave it in this form, and this would be an acceptable answer if we didn't have notation that represented this. And this is where the idea of I comes from. Square root of -1 is equal to I, and this is the imaginary unit. However, when we're talking about these types of numbers, we don't want to just forget all the real numbers, which is why complex numbers come in and are in the form a plus bi, where a is the real part, bi is the imaginary part, and the I particularly is the imaginary unit. So this is how we would write this, and then we would write our final answer here as 6i. So now where does this leave us? Well, with real numbers, the answer was always easy. We would graph real numbers on a number line. We have a system for adding, subtracting, multiplying, and dividing. We have absolute values. We have things we can do computational-wise. What would all that look like in an imaginary number system? So let's start by graphing some complex numbers. So I'll say, so now we have to think about what we know about real numbers. Real numbers were numbers that we always plotted on a number line. And this is what we did when we graphed inequalities. We would graph the number on the number line and shade all the numbers that would represent that inequality. So now we need something to do with the imaginary unit. So we decided that we, as though I was a part of the decision-making process, mathematicians decided that the imaginary unit would run perpendicular to the number line. And so this is the real number line. The x-axis is the real number line, and the y-axis is the imaginary. So this would be units of I. So when we're graphing these points, we have to look at them as coordinate pairs. So 6 plus I, remember this would be the same as 6 plus 1I. This would be like graphing the point 6, 1. So this means I'm going 6 units to the right, 1, 2, 3, 4, 5, 6, and then 1 unit up on the imaginary unit. So this would be point A. Okay. B would be the same as saying negative 3, 2. So that'd be 3 units left, 1, 2, 3, and then 2 units up, and there's our B. Let's go with C. This would be the same as negative 2, negative 2. So that'd be 2 units to the left and 1, 2 units down. That'd be C. 3 minus I, that'd be the same as 3 minus 1I, which is like graphing the point 3, negative 1. So 1, 2, 3, up 1. Or sorry, down 1, pardon me. And then we've got 0 plus 2I. Now this would be the same as 0, 2. And remember, when we're in a coordinate plane, this is graphing a point on the y-axis. So we just go up 1, 2, and that's E. And then 3 minus 0I, if we just had this point by itself, we wouldn't need the complex plane. We just plot it on the real number line. But alas, everything else is a complex number. So we graph this 1, 2, 3, and we are done. So we have a system for graphing complex numbers. What about adding and subtracting? Well, let's go ahead and look at an example. Let's talk about the computation of 3 plus I, so that's one complex number, added to 2 plus 6I. Now, we have to think that this feels like a combining like terms problem. We have the real parts. Well, the real parts are like terms. We can combine those. We've been adding 3 and 2 our whole lives. 3 plus 2 is just 5. Okay? I've meant to make this a minus to make it a little bit more exotic, so I'm going to change that to a minus. And then we got the minus 1I. So now we've got the minus 1 and then plus 6. Because they're like terms, that would give us 5I. So this total sum is, we write it in a complex number form, would be 5 plus 5I. And so adding complex numbers is the same as combining like terms if we were dealing with an average algebraic expression. We can treat the I as though it's a variable, even though it is in fact a number in this case. So let's take a look at subtraction. Let's take a look at the same two numbers, 3 minus I minus 2 plus 6I. And the same rule holds. We can combine like terms. We just have to be careful with negatives. So we got 3 minus 2. So combine the real parts. That is 1. And then remember, this is a minus 1I. So we combine negative 1 minus a positive 6. Remember, this is the same as saying negative 1 plus a negative 6, so this is negative 7I. And so when I write out my final answer, again, we write it in a complex form. This would be 1 minus 7I. And so addition and subtraction just become combining like term problems. So then the question inevitably becomes, what happens when we deal with multiplication of complex numbers. Well, that's the cliffhanger I'm going to leave you on for this video. Catch on for another video on how to do that. Until then, leave a like, comment, and subscribe, and I'll see you for the next video. Thanks for watching.